Welcome back, dear friends. In the last video, we talked about the limitation of achieving 100% efficiency. The limitation was because of the Kelvin-Planck statement. The second law says that one cannot have an engine whose efficiency is 100%. So the question is then, if efficiency of 100% is unachievable, what should be the benchmark engine? What should be the ideal engine? So the answer is it is an imaginary engine which works on Carnot cycle. So this video is to discuss the ideal cycle of the ideal engine, the best engine theoretically possible. And that best engine works on a thermodynamic cycle called as a Carnot cycle. The objective of this lecture is to discuss the Carnot cycle and talk about this ideal engine. We all know that we have taken this example of a practical heat engine. For example, the thermal power plant, steam power plant is a practical heat engine. And this practical heat engine, you know that this heat engine cannot have an efficiency of 100%, right? Because heat is rejected. This actual heat engine is not thermodynamically the best engine. It's not because this engine rejects the heat, but because this engine rejects the heat which is much more than what it should reject. This is an important point. I mean to say is that we cannot even imagine an engine which would have 100% efficiency. We cannot imagine even an ideal engine which would have an efficiency of 100%. Okay, so what is the best engine we can imagine? We can imagine the best engine as an engine which would reject minimum amount of heat, which would have a maximum efficiency, right? So steam power plant is not that kind of engine. Steam power plant is the actual engine, and it is not the thermodynamically the best engine. Similarly, the internal combustion engine, which is also a heat engine, is not thermodynamically the best engine, right? Because it is the engine which is associated with lot of irreversibilities. So heat engines, whether we talk about a thermal power plant or a regular four-stroke engine, these are practical engines whose efficiencies are much lower than what they should be. Mind well, I'm repeating this again, that even the ideal engine, the Carnot engine, cannot have an efficiency of 100%. That is because of Kelvin-Planck statement, right? So then what should be the best efficiency and what should be the best engine? So the objective again is to discuss this ideal cycle, namely the Carnot cycle. Look at this cycle, which has been schematically represented on a pressure volume diagram. So what you see is that this is a thermodynamic cycle comprising of four processes. This cycle is represented on a pressure volume diagram. The four processes are shown as process A to B, process B to C, the thermodynamic process C to D, and back again to A. So A to B, B to C, C to D, and D to A is a thermodynamic cycle. This cycle has got certain set of processes, and that certain set of processes would be the cycle representing the best heat engine if you have those processes. Okay, so what are those processes of this best engine? What are the processes of the Carnot cycle? So look at this. So the process A to B is a reversible isothermal heat transfer process. That is the first process in the Carnot cycle, A to B, reversible isothermal heat addition process. And that heat addition process happens at the source temperature. So in this case, we have taken the source at a temperature T1, we have considered the sink at a temperature T2, and we have assumed that this engine is operating between two temperatures. One is the source temperature T1 and this lower temperature sink temperature T2. Okay, so this Carnot engine is operating between the source temperature T1 and sink temperature T2. The heat addition happens isothermally. Isothermally means at constant temperature, and it happens during the process A to B. You find that during the process A to B, there is an expansion. Okay, during this heat addition, you look at this pressure volume diagram, you'll find that the volume has expanded from VA to VB. Okay, during this heat addition. So the volume has expanded from VA to VB during the heat addition process, right? And that is because of the isothermal heat addition, which has happened reversibly. The next process is B to C, which is the reversible adiabatic expansion. So it is an adiabatic expansion, meaning that the heat transfer is zero, and it is an expansion. So you see on the pressure volume diagram, the volume increasing from VB to VC. Okay. So look at this pressure volume diagram and look at the volumes which the working fluid would take after a particular process. So during VA to VB, there is an expansion. During VB to VC, there is an expansion, right? The process C to D is a compression process, and that compression has happened because of heat rejection. Okay, so there is a small correction here in the slide. So C to D is not heat addition. C to D is a heat rejection, which has to happen isothermally to the sink at temperature T2. Okay, so C to D is heat rejection at the temperature T2, which has to happen isothermally, meaning the temperature should remain constant. And D to A again is a compression process. This compression process is supposed to be adiabatic. Adiabatic meaning the heat transfer is zero. Isothermal meaning the temperature is constant. Okay, I'll come to what is reversible heat transfer. When you are talking about reversible heat transfer, for example, if you look at the process A to B. So when you talk about reversible heat transfer A to B, one thing is clear to you that Carnot engine, the temperature would remain constant and that temperature would be equal to the source temperature. So when it has to be equal to the source temperature, if the working fluid temperature has to be equal to the source temperature, it means that the temperature difference between the source and the working fluid is zero. Now you know that for any heat transfer to happen, there has to be some finite temperature difference. But because this is an imaginary engine, and we are talking about an imaginary case, an ideal case of heat transfer. And what is that ideal case of heat transfer? It is a reversible heat transfer. And what do you mean by reversible heat transfer? The meaning of reversible heat transfer is that the temperature difference between the working fluid and the source is negligibly small. The temperature difference during the heat transfer is negligibly small, very, very small. Okay, so that is a meaning. So the speciality of the Carnot engine is that the heat transfer happens not only isothermally, not only that the temperature remains constant, but also reversibly, meaning that the temperature difference between the source and the working fluid happens to be the same, almost same, that is T1. Okay, this is a very important point about reversibility transfer. The next process is a reversible adiabatic expansion. When you are talking about a reversible expansion, it means that it has to be frictionless. So you know that in real life, expansion would always be associated with friction, but in an imaginary engine, when the process is reversible expansion, it has to be frictionless expansion. And because it is a adiabatic expansion, it means that the expansion should happen without any heat exchange. Okay, the temperature would drop down when there is an expansion, right? Because there is no heat transfer, so there is a decrease in internal energy, and that decrease in internal energy would be responsible for getting you the expansion work. So there is a work obtained during expansion, but that expansion work would result in the temperature dropping from TB to TC, right? So note that P to C is reversible adiabatic expansion, and in the Carnot engine, the heat transfer is zero because it is adiabatic. The expansion is frictionless because it is a reversible expansion, and because it is expansion, the temperature would reduce. The process C to D, as I explained, is a isothermal heat rejection, and that heat rejection happens at the source temperature. Again, it is a reversible heat transfer, meaning that the temperature difference between the working fluid and the sink is zero. So it is not simply that the temperature is constant. The important point is it is not only constant, it is also reversible, meaning that the temperature is same as the sink temperature, almost same as the sink temperature, and that makes the heat rejection reversible. Okay, so this is an important point again. So the speciality of a Carnot engine is that the heat transfer is reversible in both the cases, that is during the heat addition as well as heat rejection, and it is not only reversible, it is also isothermal. The next process, the last process, is reversible adiabatic compression. Adiabatic meaning again the heat transfer is zero, and because it is reversible, the compression phenomena has to be frictionless, and because it is compression that would lead to, because you need to do certain work on the system. Compression work means work has to be done by the surrounding on the working fluid, and as a result of which its internal energy would increase, the temperature would increase. That is an important point to be made. So what we have understood is that the practical engine, that is a steam power plant, or let us say your 4-stroke engine, 2-stroke engine, all these practical engines are not the best engines from a thermodynamical perspective, because the processes there are irreversible. What makes Carnot engine the best engine is because it is a reversible engine. And by reversible engine, we said that all the processes of the Carnot engines are reversible. There is a reversible isothermal heat transfer. There is a reversible adiabatic expansion. There is a reversible isothermal heat rejection. And there is a reversible adiabatic compression. So all the processes are reversible. And that is the reason why it is the best engine without any irreversibilities. Okay. So note that, and this is a very important point, that Carnot engine, though it is a best engine, its efficiency would always be less than 100%. That is because no engine, even a Carnot engine, can have an efficiency of 100%. That is because the Kelvin-Planck statement clearly says that no engine can have 100% conversion of heat to work. Okay, this is the important point. Then what is the distinguishing feature between a Carnot engine and practical engine? The distinguishing feature between a Carnot engine and practical engine is that the Carnot engine rejects the minimum amount of heat. The Carnot engine has the best efficiency. Thank you very much. Bye.